Today, we're taking a deep dive into the captivating world of the gaseous state. From the mesmerizing dance of gas molecules to the complexities of critical constants, we're going to unravel the key concepts and phenomena that govern gases. So, fasten your seatbelts as we embark on this exhilarating journey. Part 1: Kinetic Theory of Gases. Picture a bustling crowd at a marketplace. Gas molecules are like these tiny individuals, moving about ceaselessly. The kinetic theory of gases describes their behavior. It's built on four main postulates. 1. Molecules in motion. Molecules are in constant motion, colliding with each other and the container walls. 2. Negligible volume. Molecules are so tiny that their volume is negligible compared to the space they occupy. 3. Elastic collisions. Collisions are elastic, meaning no energy is lost when molecules bounce off each other. 4. Average kinetic energy. The average kinetic energy of molecules is directly proportional to temperature. Part 2: Deviation from ideal behavior, van der Waals equation of state. Now, in reality, gases don't always behave ideally. They can deviate from the ideal behavior due to molecular attractions and volume occupied by molecules. Enter the van der Waals equation of state. This equation, formulated by Johannes van der Waals, factors in the finite size of molecules and their interactions, resulting in a more accurate description of real gases' behavior. Part 3: Critical temperature, pressure, and volume. Every gas has its limits. Meet the critical point, the temperature, pressure, and volume at which a gas becomes neither liquid nor gas but a mysterious state in between. Critical temperature. Think of critical temperature as the point where a gas puts on its I won't turn into a liquid cape. It's like the highest temperature a gas can handle without turning into a liquid, no matter how much you heat it. For different gases, critical temperatures vary widely. Carbon dioxide, for instance, has a critical temperature of around -31.04 degrees Celsius, -23.87 degrees Fahrenheit, while water's critical temperature is a steamy 374.15 degrees Celsius, 705.67 degrees Fahrenheit. Critical pressure. Now, picture a gas being pushed and squeezed, almost like it's resisting turning into a liquid. That's where critical pressure comes in. It's the amount of pressure needed to make a gas and its liquid sidekick exist together at that supercool critical temperature. The critical pressures of different gases exhibit remarkable variability. For hydrogen, the critical pressure is an astonishingly low 12.8 atmospheres, whereas ammonia's critical pressure is a much higher 111.3 atmospheres. Critical volume. Lastly, consider this as the minimum personal space requirement for a gas before it starts thinking about turning into a liquid. Imagine a gas inside a container, huddled up at the smallest space it can without crossing over into a liquid state. That's the critical volume, a unique measurement for each gas. Like critical temperature and pressure, critical volume varies among gases. Helium boasts a particularly low critical volume due to its unique atomic properties, while sulfur hexafluoride, a heavy gas, has a higher critical volume. So, whether a gas likes to stay chill like helium with a tiny critical volume or goes all spacious like sulfur hexafluoride with a bigger one, these critical properties give us a sneak peek into how gases behave at their absolute limits. Part 1: Boyle's Law, Pressure and Volume Tango. Imagine you're squeezing a balloon. Boyle's law tells us that if you keep the temperature constant, the pressure and volume of a gas are inversely proportional. As you decrease the volume, the pressure increases, and vice versa. This law is the key to understanding how pistons work in engines and why scuba divers need to equalize their ears underwater. Importance of Boyle's law. Boyle's law is at the heart of breathing apparatuses, air conditioning, and even the inflation of car tires. It shows us how to manipulate pressure and volume to achieve desired results, making it essential for everything from medical equipment to industrial processes. Part 2: Charles's Law, Temperature and Volume Relationship. Imagine a balloon floating in the sky, getting warmer with the sun's rays. Charles's law tells us that when the pressure is constant, the volume of a gas is directly proportional to its temperature. As the temperature increases, the volume expands, and as it cools, the volume shrinks. Importance of Charles's law. Charles's law guides the design of hot air balloons, airbags, and even the inflation of tires. From weather forecasting instruments to household appliances, this law helps engineers and scientists understand how gases respond to changes in temperature. Part 3: Gaseous law, exploring the temperature-pressure connection. Imagine a balloon left in the sun, warming up as it soaks in the rays. Gaseous law reveals a fascinating secret: when the volume is constant, the pressure of a gas is directly proportional to its temperature. As temperature rises, pressure dances to the same tune. Importance of Gaseous law. Gaseous law shines in engines, helping us understand combustion and the explosions that drive our cars. It's a crucial puzzle piece in weather forecasting, where changing temperatures create shifts in atmospheric pressure. From aerospace engineering to weather science, this law is a guiding star. Part 4: Avogadros law, volume and amount of gas relationship. Imagine a room filled with gas molecules. Avogadros law tells us that, at a constant temperature and pressure, the volume of gas is directly proportional to the number of molecules it contains. This means that if you have more gas molecules, you'll need more space for them. Importance of Avogadros law. Avogadros law is the foundation of stoichiometry in chemistry, allowing us to balance chemical equations and calculate reactants and products. Part 4: Ideal gas law, uniting all laws. It's the ultimate formula that links pressure, volume, temperature, and the number of molecules together. PV equals nRT. Dalton's law of partial pressures. The total pressure of mixture of non-reactive gases at constant temperature and pressure is equal to the sum of the individual partial pressures of the gases. Applications of Dalton's law of partial pressure, unveiling gas mixtures magic. Part 1: Air composition and breathing. Think about the air you're breathing right now. It's not just one gas, but a blend of different gases. Dalton's law comes into play here, helping us decipher the unique contribution of each gas. From the crucial oxygen that sustains life to the nitrogen that fills the volume, Dalton's law lets us understand the individual pressures of these gases in the air we breathe. Part 2: Scuba diving safety. Imagine descending into the deep blue sea for a thrilling scuba diving adventure. As you go deeper, the pressure increases. This is vital for calculating the right mixture of gases in your tank, including oxygen and nitrogen, to prevent the dangers of nitrogen narcosis and decompression sickness. Part 3: Medical oxygen therapy. Patients in need of extra oxygen receive it through specialized tanks or masks. Dalton's law ensures that the partial pressure of oxygen is increased while keeping the other gases at their original levels. This targeted delivery of oxygen aids in respiratory therapy and recovery. Part 4: Atmospheric pressure and flight. Let's take to the skies. When aircraft soar to higher altitudes, the air pressure drops. Dalton's law reveals the secret behind this phenomenon: each gas in the atmosphere contributes a portion to the total pressure. Pilots and passengers breathe a mixture with adjusted oxygen levels, ensuring safety and comfort during flight. Part 5: Gas chromatography. In laboratories, scientists rely on Dalton's law for a technique called gas chromatography. This method separates and identifies components of a gas mixture. By understanding the individual pressures of gases, researchers can analyze complex mixtures, identify compounds, and even detect trace amounts of substances. Limitations of Dalton's law of partial pressure. 1. It is applicable only to inert gases like N2 and O2, N2 and Cl2, etc. 2. It is not applicable to chemically reactive gases like H2 and Cl2, CO and Cl2, etc. Graham's law of diffusion/effusion. Diffusion, ability of a gas to spread and occupy the whole available volume irrespective of other gases present in the container. Effusion, process by which a gas escapes from one chamber of a vessel through a small opening or an orifice. The rate of diffusion, R, of a gas at constant temperature is directly proportional to its pressure. Applications of Graham's law of diffusion, unraveling the dance of molecules. Part 1, The essence of Graham's law. Imagine a room filled with the enchanting aroma of your favorite perfume. Graham's law reveals a hidden symphony. The rate of diffusion of a gas is inversely proportional to the square root of its molar mass. In simpler terms, lighter molecules waltz through space faster than their heavier counterparts. Part 2, Perfumes and Aromas. Ever wondered why you can smell a spritz of perfume from across the room? Graham's law provides the answer. Lighter fragrance molecules, with lower molar masses, diffuse quickly through the air, reaching our noses faster. This is why a gentle scent can spread and enchant our senses. Part 3, Respiratory exchange. Consider the air we inhale. It's a blend of gases crucial for our survival. Graham's law whispers to us that lighter gases like oxygen, with lower molar masses, diffuse into our lungs faster than heavier gases. This principle underlies efficient gas exchange during respiration. Graham's law guides engineers in designing efficient systems for gas separation, such as distillation processes. It helps optimize production, save energy, and ensure product quality. In medical settings, Graham's law influences drug delivery. Lighter gas molecules, like those in anesthetic gases, diffuse rapidly across cell membranes. This knowledge helps anesthetists control the speed of induction and recovery during surgeries.